We want to finish up this chapter by considering several useful amplifier stage combinations. So we begin with combining the common collector or common drain, otherwise known as the emitter follower or the source follower, with a common emitter or common source amplifier. And here we see some permutations. First, the two bipolar stages, then two MOSFET stages, and then lastly a bi-CMOS stage. We won't be analyzing these at this point. We're just going to look at some of the characteristics, what's the advantages of doing this. So there are two main advantages of the common collector to common emitter configuration. Recall that the input resistance of the common of the common collector is that, like for the bipolar junction version, the resistance reflected from the emitter back to the base is increased by beta plus 1. So whatever the input resistance was to this common emitter stage, when we look in through this common collector stage, we see a resistance that's beta plus 1 times the Rn of the common emitter stage. So we see an input resistance, increased input resistance, and therefore the overall voltage gain is increased, particularly when R sig, the resistance of the signal source, is not small. And then a second benefit that might not be appreciated at this point is that there's a much wider bandwidth for this amplifier pair than for a common emitter amplifier by itself. And the clue to that, or at least I think we can get an idea of what leads to this. There is a capacitance between the collector and the base, which is not very large, but there is a multiplying effect in that a small change in the base voltage will produce a very large change in the collector voltage. And so the polarity of the feedback is a negative one, such that if the transistor turns on harder, the collector voltage falls. What will tend to happen is current will flow from the base through that capacitance to the collector side. And so the flow of that current is actually stealing or robbing base current, which will have the effect of turning off the transistor and therefore slowing down the fall of the collector voltage. So you can imagine the higher the frequency that you are trying to drive the base, the faster the collector voltage is slewing up and down, and therefore the greater the current that will flow through this capacitance, because the reactance of the capacitance goes down with frequency. So eventually the current flowing through that capacitor will be substantial enough that it will take a significant amount of current away from the base and effectively reduce the voltage gain of this output transistor. So what we need is a better voltage source connecting or driving this base. If I had an ideal voltage source here that I could drive at whatever signal that I wanted to, then it wouldn't matter how much current was being demanded of it through this parasitic capacitance, this Miller capacitance. The voltage source would be able to supply it. But the problem is that with the standard common emitter amplifier, there is a source resistance, R sig, and that R sig, when current is demanded of it through this Miller capacitance, that causes voltage to drop at the base. And so what we need is a lower source, impedance source, to drive the base of our common emitter stage, and that's precisely what the common collector stage does. It lowers the resistance. If you look back into here, you will see, and if we have R sig over here to a voltage source, this resistance that we'll see is going to be Re of this transistor 1 plus R sig divided by beta plus 1. And so we will have a much lower resistance than if we didn't have that common collector stage. With only the common collector stage, the resistance we'd see looking back there would be R sig. So this is what contributes to a much wider bandwidth. Moving on to the common drain, common source stage, it has the same, well, it has the same greater bandwidth advantages. It does not improve the input resistance because for a MOS-based common source amplifier, the input resistance is already infinite. But it does improve the bandwidth, and that's why it is useful. And then lastly, we have the bi-CMOS configuration. It has an infinite input resistance. That's an advantage over the BJT version, and there is an advantage of the common drain, common emitter over the purely MOSFET implementation here in the middle, in that there is generally a higher GM2 compared to MOS only, and that goes back to the GMs achievable by bipolar transistors are greater than what's achievable with a MOSFET, and so by having a bipolar as the second, as the common emitter amplifier stage, we can achieve greater gain than if we had used a MOSFET common source amplifier stage. Okay, let's move on and look at a couple, two more things, I think. Let's look at the Darlington configuration. This is a popular bipolar junction transistor pairing, particularly as you get to output stages, power stages in an amplifier. And connecting two transistors together as seen here, where the emitter of the first one feeds the base of the second, produces a composite device that behaves like a single transistor but having a forward current gain of beta 1 times beta 2. So you have much higher current gain. The drawback is that the VBE, effective VBE of this composite device is now approximately 1.4 volts as opposed to 0.7. If you are using this in the common collector configuration, like I show here, then it has positive impacts for both the input resistance looking into that amplifier and the output resistance looking back from the load. The input resistance is going to be basically beta squared times RE in parallel with whatever R load you'd have out here. Okay, so you have an increase in Rn by a factor of beta. The exact expressions are there on the right, but it's effectively an increase of beta over a non-Darlington version. And the output resistance, when you look back in, would find that the output resistance is reduced by, or at least the resistance from R sig that transforms itself and appears at the output is reduced by a factor of beta. So you decrease the output resistance and you increase the input resistance, and those are both good things. There is another version of the Darlington pair. This is called the complementary Darlington pair. This will actually be used I believe, in the final power audio amplifier project that you will be building. And this behaves just like the original Darlington pair. You effectively get a current IC here that is equal to beta 1 times beta 2 times the input base current. There is a resistor there that does not factor into the main operation of the device, but it does help to keep Q2 off when there is no base drive to Q1. And the main trade-off is that from the conventional Darlington configuration, the non-complementary version, is that the VBE is restored back to about 0.7 volts because going from the base of the composite device to the emitter only has to travel through one VBE junction. The trade-off, though, for that is that the VCE SAT of this composite device is much higher compared to the non-complementary Darlington pair. The non-complementary Darlington pair would have a VCE SAT that's 0.1, 0.2, just like a regular transistor. Here, saturation, if you look from collector and work your way down to the emitter, you would have 0.7 volts in the VBE junction of Q2, and then you could have 0.2 volts, say, in VCE SAT of Q1, and that you add that together and you get about 0.9, 0.8, 0.9 volts for VCE SAT. So that means if you're using this in an output stage and the collector is tied up to the supply, then the emitter cannot come up as close to the supply as it could if you had the non-complementary Darlington pair. Okay, lastly, we're going to look at, this is the last topic here for this section and for Chapter 7. And here we're combining a common collector and a common base. So again, what's different here from what we just did? Go back up. Here we were looking at a common collector, common emitter. Now we're going to look at a common collector, common base. So we're keeping the same front end stage and replacing the output stage from a common emitter to a common base. And this will become very relevant for the next chapter, where we will look in detail at a particular pairing that we call a differential pair, a differential transistor pair. So what I've done here, what we've done is the common collector stage made up of Q1 would have a current source, I, and the common base stage would have a current also, I. And what we've done is we've combined those two together, because after all they're running in parallel, so we might as well just put them together. Now this current source up here may be confusing to you. You can replace it with a resistor, and that works fine. And now that looks like a more familiar common collector feeding a common base, and the same principle of operation applies there. So what are the characteristics of this stage? Well, we'll look at it in more detail in the next chapter, because actually this is what we'll be studying for that entire chapter. But essentially we have a higher input resistance, because we get this beta plus 1 multiplication of whatever resistance is in the emitter of Q1, and then reflected over to the base. Now, what resistance do we have in the emitter of Q1? We would have an RE1, and we can't go through this current source here, because that's the current source. When you signal level, you turn that off. It's an open. But we do have a path back here. We have an RE2 back to ground. So the input resistance ends up being, the input resistance ends up being beta 1 plus 1 times the sum of the two emitter resistors, small signal emitter resistors of Q1 and Q2. When this is designed, typically the Q1 and Q2 are matched. So imagine that at VI equal to 0 volts, the base of Q1 and the base of Q2 are at the same voltage. Their emitters are tied together, and now you're pulling 2I from both of them together. And there's a symmetry, and so current will actually split between the two, and each transistor will carry half of 2I. So each transistor will be biased at a current of I. And so the RE1 and RE2 will actually be equal, and they will be equal to the V thermal over I. So if that, for instance, if 2I was 2 milliamps, then we would have 25 ohms for RE1 and 25 ohms for RE2. If beta was 200, then we would have an input resistance of approximately 200 times 50 ohms, which would be 1 kilo ohm. Not very high, but another characteristic of this amplifier is that VI, the quiescent operating point for this amplifier is VI being equal to whatever the base of Q2 is, and it's grounded in this case. So when VI is equal to 0, the currents are splitting evenly, and we can think about that being the operating point. And that's unique from any of the other amplifiers that we've looked at in the past, because we've always had to bias up the base or the gate of a transistor. Now we got away from that a bit when we put a decoupling cap. We were able to bias the gate or the base up with some pull-up resistors or resistor dividers, whatnot, and then put a coupling cap so that VI could be zero reference, didn't have to have an offset. But here this is DC coupled, and VI sits at, or is at a nominal quiescent voltage of 0 volts. So that is another characteristic of this amplifier. The output resistance of this amplifier will be just like a common base or a common emitter. It's basically RC if we're building this discretely, or else we'd have an output resistance that involved the RO of the transistor Q2 as well. The middle circuit is just an alternative version of the common collector, common base, and then where it uses complementary devices. And then the third one here is a MOSFET implemented version. And again, this current here, this current source could be a resistor. We can take a quick look at the gain of this. We'll go through this in detail in the next chapter. But if we look at small signal, let me draw a small signal version of this amplifier. So I'm going to use the T models for each of these transistors. When we look at the small signal, the 2I is turned off. I'm going to use RE. I guess I'll do RE1 and RE2. This will be grounded. We have an input VI here, and this is going to be alpha 1 IE1, and we have an RC. And let's see, this is going to be grounded. Interesting. That'll be grounded. And this will be this will be alpha IE2. Okay, so interestingly here we've got, when we look into VI here, we see I should say that the current flowing this way here is going to simply be VI over the sum of RE1 plus RE2. And this is precisely equal to IE1, but it's equal to minus IE2. And the voltage at the output, VO, will be equal to minus RC alpha times IE2, and IE2, or minus IE2 then, we can substitute in, we'll have alpha RC RE1 plus RE2 times VI. This leads us to VO over VI of approximately RC over 2 RE. Oh, what did I do? I made an error here. Okay, there we go. So I had a mistake in my writings below. So the voltage gain is essentially, it's just a factor 2 off of the voltage gain that we would expect from a common base amplifier. So collector resistance divided by the incremental emitter resistance. But again, there are some significant differences in this case. The input resistance is beta plus 1 higher than it would be for a common base amplifier alone. And additionally, the quiescent operating point is for VI to be at 0, not to be at some DC voltage. Of course, you could switch this, you could change this if the base of Q2 was not tied to ground, but instead, if we tied it to some other voltage, say 1 volt, then the quiescent point would be VI equal to 1 volt, and so this is a big advantage. I'll give you a kind of a lead for what's coming, and to say that actually this is the front end of most operational amplifiers. So if you have a bipolar based operational amplifier, what they'll do is they will not ground the base of Q2. The base of Q1 and the base of Q2 are the two inputs, the inverting, non-inverting, or non-inverting and inverting, depending on what follows in the subsequent amplifier stages. But those are your two inputs, and it's the quiescent point is when those two base voltages are at the same voltage, right? And any differential voltage is what actually causes amplification. And although we haven't looked at it yet, when we do, lift the base of Q2 from ground and consider it as a separate input, and now we look at VI1 minus VI2, we'll see that this is actually a differential amplifier, and that will be the basis for the front end of an op amp.